I'm very glad to introduce Maurice Duits, who is professor at ETH in Stockholm. And so he's one of the laureates of our Chaire d'Excellence of the Fondation Séance Mathématiques de Paris. And he's welcome in LPSM. And so he's here for 12 months. He's been here already since September. And so until August or something like this. So yeah, we're very glad to have this series of 7 lectures. 2 will take place here, and then we'll go in the opposite building. So please.
Okay, thank you very much. It's a great pleasure to be here. Special thanks to the Aztec Diamond to give me this opportunity to be in Paris and also to present this lecture for you. So I have prepared a course around the Aztec Diamond, which is a particular model of a random tiling model or random diamond model. We will not just see the Aztec Diamond only, but it will be the canonical example that I plan to put everything in the course on. And I will also take a slightly different perspective than maybe some of you are used to. I will take an analytic perspective. My background is really from analysis, so I like to see the analytic structures in these models. Random tilings have very exciting properties, combinatorial, probabilistic, or many interesting things that we will see. I will touch upon a few, but my interest is mostly from analysis. So I hope also it will give you an alternative perspective, even for those that already are used to the other types of perspectives. So before I come and say anything, let me just say a few words about the course. So let me just first say some practicalities. So as Beatrice already said, it's going to be 7 lectures. The poster has 9 dates. So 2 of them are going to be cancelled or used, upon how you and I feel. We can see. But at least I have fixed sort of the first 4. I will guarantee that these will take place unless sickness or anything else prevents me from coming. But okay, so the first 2 will be on today, the 15th, and then next week, the 22nd, on Thursday. They are from 2 to 5. Then we will move to another place, but also another day, right? So it will be on Tuesday, and also a different time. It will be in the morning. So yes, then you can judge which one was the better, when I was the most fresh. Anyway, so the first 4 lectures, they are basically fixed. Then there will be 3 more lectures. They will also be on Tuesday, and I am not sure yet. I think they will just be on the 10th, the 17th, and the 24th, but I will confirm this very soon. Okay. Okay. So what I want to do is that actually my plan is maybe a little ambitious, but we'll see how that goes. My plan is actually to have these 7 lectures also around each of them around a particular topic, especially towards the end, about a particular topic. So in case you will miss a few lectures, you still drop in, because I aim to present it it's my ambition. We'll see if it works. That all the lectures are sort of self-contained. I will use the blackboard mostly, but today I will actually use some slides because I thought it might be a nice idea to start slow with a colloquium style lecture before, to motivate what we're going to do, why we are interested in the Aztec Diamond, and what I want to do in this course, and then start the hard stuff. I also want to say that there is a homepage. I made a homepage, so let's see. Now, if I go here, if you click that link, you will see a homepage. It's a little strange how it's organized here. Do you see my cursor? No. Is there anything working? No, there's no. Yeah, I should of course go like this. Can I go like this? So here I have, this was the abstract for the course. Here I will also update times, and you'll see basically a preliminary overview of topics. I will come back to that later. Also the time, also indicate the place. And moreover, I will also upload lecture notes. I will do this as mode to provide some material later. There is no real nice book that I could use. Maybe there will be after the course, but you know, again, maybe I'm too ambitious. I will provide some lecture notes. So for the lecture notes for today, they're already there. It's a 60-page document, but I don't intend to cover anything, so there will be extra material. I will also say that if it's clear that it's sort of written by me, then it's a little disclaimer that it's a draft. So it could be incomplete or mistakes. Mistakes, I would be very happy if you point them out so I can correct them. That's just a little disclaimer. The notes for today is just a merging of several notes I use for some other things, so I don't know if it's if it turns out that let me know if there are mistakes or anyway. Yes, so that's important. You can look at it there. I also think it might be a good idea. I will upload as much as possible on this webpage. This is hosted at the KTH site, and I have gotten recently a message that KTH doesn't want us to use any personal web pages. So, and they said that within a month everything will be erased. Then there was a lot of protest against this, and now it's not so clear what's going to happen. I hope it will not be erased. So if it does, I will quickly upload something. But maybe also for this reason, it might be good actually to have a little mailing list. So anybody that wants to take active part in the course, I would like to ask them to send an email to my email address here. Then I can make a mailing list and can use that for giving extra material or making some comments, or perhaps if something needs to be changed in terms of infrastructure last minute, then I can also say that. So that's maybe a good idea if you plan to be here until the end of the course, or be part of it at least, then send me an email, then I'll put you on the mailing list. Okay, any questions there? No, I guess not, or maybe there will be, but you can always send it to my email. Okay, so my plan for today is that I think I have to go back to this here. Yes. So my plan for today is that I want to give a colloquium style introduction to the Aztec Diamond and why we care about it, and a little bit the questions that we're going to analyze. I prepared that with slides, so we will go through that. I'll show some nice pictures, some results, some theorems that maybe some of you already know. I chatted with some people just before the lectures, and I think some of the people already know some things I will say today. I have intended it for non-experts, so I will really start from scratch. And after one hour roughly that I have motivated what I'm going to do in the course, I will start going on the blackboard. Okay, so tilings of planar domain. So first of all, what is it and what are we going to do? So a tiling is really just as you think as it is. You have a certain domain, a planar domain. It could be anything, maybe a square or something, and we'll see some examples. And we have given types of tiles, and we're going to cover that domain in such a way that the whole domain is covered and no tiles overlap. Just as on the bathroom, you put the tiles on the bathroom wall, you cover the whole wall with some shapes, and no space is on tile, and no tiles overlap, unless you have a very amateuristic worker. Anyway, so that's what we're going to do, and of course you could do this with many different shapes. I don't want to go to anything exotic. I want to take basically two types of two different families of shapes. One of them are just rectangles, or they're called dominoes. They could be vertical or horizontal. And the other type of shapes, they are lozenges. Yeah, the name lozenges comes from, I don't know if you know this, but these are also lozenges, are also some cough medicine, and then there used to be some old-fashioned cough medicine. I don't know, some people know this, some people, they say it's trivial, some people don't. There is some old-fashioned cough medicine that has exactly these shapes, and they're quite delicious, I have to say. I don't know if they're still common here in France, actually. I haven't seen them. Anyway, so these are the two different families of shapes, and I will motivate why in a minute. So I'm not going to look at very exotic shapes at all. Okay, so, and then the domains, well, we could think about maybe, let's take just the simplest possible one. Let's take a square, or maybe a square with some corners taken out. And then I'm just going to cover these domains by this kind of points, okay? So this is this is just what a random tiling of a planar domain is. In this case, with domino tiles, okay? And you see that here, it's not always clear that it's possible that you can tile a domain, right? So you can ask yourself, if I have a domain, can I always tile it so that nothing is left? This is not always possible. I will not care so much about this question. Okay, I will always look at domains that I already know it's tileable. A little bit more interesting question for me is that if you know that it's possible, how many ways can you tile? That's also a very interesting question, and I will not say so much about that, but it will play a role sometimes in the course. And for lozenge tilings, that's the other type of tiles that we will see in this course. For example, we take a hexagon or maybe a slightly more complicated shape. Yeah, you can tile these domains by this kind of shapes. And here actually the lozenges, they are somehow a little bit nicer, because if you look at it, you might recognize this as a three-dimensional picture, namely that there are some boxes that are stacked in some special rows. This is something that is sort of nice about lozenge tilings. They have a 3D picture right in front of you. With the domino tilings, there is a 3D picture also, but it's not so, it's a little hidden. Okay, and then we will talk about this. Okay, so now these pictures that were pretty gray, I want to put some colors on these pictures. And for dominoes, there is a nice way of, instead of just having boring shapes, actually putting some colors in these pictures to make it visually attractive. And actually it also gives me immediately an opportunity to mention that these kind of tilings are related to what we call matchings of bipartite graphs. So let me just start first with a particular domain, and I'm going to tile it with dominoes. It will be very convenient to put a checkerboard on the domain with black and white squares. And then you'll see that the dominoes, they will always cover exactly one black and one white domino. So actually, if you ask about a particular domain and you would put your checkerboard on that domain, you already see that the amount of, if you ask if it's tileable, the first thing you can do is check if there is just as many white as there are black squares, because it needs to be the same, right? Okay, and this also gives us an alternative way, and we will do this maybe sometimes, but not so much. But I do think it's important that I point this out now. This also allows us to do the following. On the black square, I'll actually just represent it by this cursor is not visible, right? No, if I if I have a cursor, I don't see it on the screen, right? No. There is no pointer, or
I can go and see.
Okay, maybe there is a pointer. Well, anyway, so there is this the black and the white vertices, and you see that each domino sort of connects a black to a white. So if I just indicate this by blue lines, then I actually see that there are nice bonds between black and white vertices. And actually this tells me that I'm actually looking at a bipartite graph. We have black and white vertices. And each tiling is actually saying that we have a matching of that graph. Okay? So the random tilings that I will study in this course, they can always alternatively be viewed as matchings of bipartite graphs, perfect matchings of bipartite graphs. Okay? And then for the domino tilings, you will always have that this is a part of the square lattice. For the lozenge tilings, you have the hexagonal lattice. Okay? But just already a disclaimer, I know some people already told me they work on diamond models, so they know this very well. There is a little disclaimer. I will not really use like Castellan's theory in this course, so if you're used to that, it would be good to know because you will learn something new. Okay, so that's just something I wanted to say. Okay, but it also gives me an opportunity to actually do the following.
In the side place.
I need to turn around. Yes. Oh, okay. Yes.
Ah, you have a PowerPoint.
Need help, just.
Avec les scales, when you go. It doesn't work.
No, it doesn't.
Okay, so get one to go for one.
So it actually shows that we don't, for dominoes, we don't have two types of dominoes, we actually have four types of dominoes, depending if we are, for the vertical ones, depending if the black or the square is up or is below. Okay, and if they are below, I will color them yellow. If they are up, they will color them blue, and vice in the same way for the horizontal dominoes. Okay, so that actually gives it a very nice way of looking at things instead of these kind of black, the white and gray pictures. So the black and white pictures, we can get some nice colors, and this will be very convenient in a minute. Okay, so that's just everything I wanted to say about just general random tiling models. There's different domains you can consider, and people do consider different type of domains. In this course, I will look. Yes, you had a question? Sorry. Sorry. Okay. In this course, I will look at a very particular domain in special. We will see also different domains, but this one is the one that I basically will design the course around. And this is the Aztec Diamond. And it looks already always a bit special, but actually it's a very, very beautiful model that has lots of symmetries and has lots of sort of combinatorial, analytic, algebraic structures hidden there that we will see in this course. Okay, so it's a little bit particular domain. It's the domain on the right. It's no longer a square, but it will have this strange shape. So we have it's a diamond, but the sides of the diamonds have this staircase behavior. Okay, and these staircases, they might sort of remind you of the shapes of these Maya temples that you may know about. And since it's it looks a little like a Maya temple, we call this an Aztec diamond. Okay, don't shoot me. I don't know. It sounds. I think the reason was that the Aztec diamond sounds a little bit more attractive than the Maya temple. But anyway, and those of you that were speaking before, I really like to say that a few years back, I actually had the opportunity, the real great pleasure to be in Mexico and talk about the Aztec diamond, and I was very excited. And in the room, there were lots of people, local people, that were looking at me like, no, this is really a bad name. Okay, so there is nothing Aztec on the Aztec diamond, but we will call it the Aztec diamond. Okay? Okay, very good. So this is a very strange shape. I hope it's clear to you immediately that it's possible to do actually a tiling of this domain. But if not, then I will just convince you now. Here is a particular tiling of the Aztec diamond. Okay, and we have just two shapes, but we have four colors depending on the position of the black and the white square. Okay, so this is the model that I will study. I will call this the Aztec diamond of size n. Okay, n equals 4. But our main interest will be when n is actually very large, when our domain is very large. Okay, and I will come to that in a minute. Okay. I actually just but this is a similar. This is a USB. I can do it maybe like this, but this is. Yeah, I don't know. Answer. Why doesn't it? I will do it. No. No. Okay. That's okay. It's okay. It's okay. I think it will be fine. It's okay.
Sorry.
No worries. No. Right. So this is the Aztec Diamond. This is the shape that we will have. So it's the Aztec Diamond of size n. Okay. It will be convenient, and I will do this a lot. Actually, we see this in pictures to actually rotate this, so you will actually see this picture maybe more often than you see this picture. It's just the same thing. It's just rotated. Okay, and this saves space. If you ever wrote a paper, you will notice it saves space. But it's also a convenient perspective, especially for next week. So what about randomness? Okay, so now we play the following game. We're not going to ask questions about whether doing is tileable. We have the Aztec Diamond. We know it's tileable. There is at least one tiling, but there are many tilings. And then you can ask yourself, how many tilings are there? And there is a very beautiful answer to that. It's just 2 to the n times n plus 1 over 2, where n is where n is the size of the Aztec Diamond. So really it grows very fast. The larger the n is, it will grow super exponential to get the number of tiles. It's okay. It's okay. It's okay. It's okay. Okay. So then you can ask. Okay, we have many possible ways of tiling. How does a typical tiling look like? So put all the tilings in the bag and now pick one uniformly at random. What happens? Well, if you take a small tile here, I actually really generated uniformly at random, and okay, yeah, I don't know if you see anything, but it's just okay, nice pictures, but I don't see anything so much, no structure. Now let's increase this. Let's increase this to 5. Okay. Well, I don't know if you see anything. Not so much yet. Maybe you see one thing is that each corner has basically one color of tile already. Like if you look at the here there is a green in the right corner and a blue one, and then there is a red and there is a yellow in each of the corners. And this will actually be typical because when n goes larger, this effect will be stronger and stronger. And what you will see is actually that most tiles in the corner are frozen. And when you go to n equals 100, you really see these pictures happen. You see this, okay? And now let's take n is 500, you really see this, okay? And this is a beautiful picture. Now, I don't know how many of you already have seen this picture before, but if it's the first time that you see this, this is a bit surprising because it doesn't look so random, right? But it's weird because it's really taken uniform at random. So what does it actually mean? It actually means that if you take, that most of the tilings, not all, but most, the vast majority of tilings will have frozen corners. If you would put all of them and you go through them, then you will see much more often tiles with a frozen corner than tiles that actually have a disorder. And this is an effect of this very strange stair-shaped condition. Okay? And I will get back to that later. Okay? But this is an interesting picture, and in the first part of the course, what I aim to do is to just understand this picture. I really want to prove to you that this will appear. I will show that there is that when the size of the Aztec Diamond goes to infinity, we will have frozen corners, and there is some kind of circle. Actually, there is a circle. It's called the Arctic circle, where in which all of the randomness is. Okay, that's the first thing. I will really show you that this will appear using some analytic methods of complex analysis. Not only that, I will also look at fluctuations. There are very interesting pictures. If you squeeze your eyes a little bit, then you basically see a deterministic picture, sort of a limiting configuration, and then there is some fluctuations around. And one of the points of my point is that these fluctuations are very interesting. Okay, so I want to say a few words more about this. So this is basically the first, one of the main goals of this course. It's not the only one, but one of the main goals, and especially in the beginning, is I want to show you how this happens, how this works. Okay? So I will prove that there is a disordered region, that is a disk. We will look at the interface between frozen and disordered. This is a very interesting regime. We will study it. I will look at processes in the middle. I will say like, okay, I will be a bit more precise in a little bit. And one of the nice things about the Aztec Diamond is that it touches the beautiful mathematics. There are some very beautiful structures that you don't see yet that I will try to explain. And they can be used to prove these things. So along the way, we'll also see very nice mathematics, and particularly analysis. Okay, so but before I come to that, let me go to the question like, why do we do this? And why do we care? Why do we look at a model with a name that is not even real? So why do we care about this? Well, I mean, first of all, this is a very nice fact in probability. Let me actually go back to a classical probability. I mean, the fact that when I increase the size of the Aztec Diamond, that actually some randomness disappeared, or actually things look a little bit more deterministic, is something that you already have seen very well. Okay? And that's what we call the central limit theorem of probability theory. Okay? So, and actually it goes back, and I'll do this, I'm not going to underestimate your intelligence here, I just want to have a point with this slide. Let me go back to the classical CLT and go really a few hundred years back by the work by Lauréat and Laplace, and just look at Bernoulli trials. Let's toss a coin a number of times, yes, and look at the number of times we get hat, right? Okay? Just the Bernoulli trial, a repeated Bernoulli trial. Okay, we know this model very well. Just a simple model from probability theory. Now we know that the probability of having k hat after n tosses will be just a binomial distribution, okay? And if p is a half, then we have a fair coin, right? This is just a very simple standard thing. And what happens there now, when n is large, is exactly the same question as I did for the Aztec Diamond, and we know the answer very well. If you would draw sort of the probabilities, here I drew the probabilities on the left for a small m, and then I let n go to infinity, this Bernoulli distribution really converge to a beautiful Gaussian, and this is of course a very well-known fact, right? And actually what the Laplace theorem says is actually that the binomial distribution really, you can just do some analysis and really show that it looks like a Gaussian. Okay, and it was the first instance of a central limit theorem. Okay, and this is sort of the same effect, right? When you have a random system, if n is if you do only a few tosses, then okay, then nothing really happens. But when n is large, some things start to concentrate, and the fluctuations are Gaussian. Okay, and this is of course this can be, you can just compute it in this model, right? But then you can actually generalize it. This is, of course, a universal phenomenon. This is what we call the CLT in probability theory, right? When you have the independence makes it work that if you have a law of large numbers, if you have a number of random variables, the random variables, the average will converge to the mean very fast even, and the fluctuations are given by Gaussian. Okay. Now, why do I do this classical? Result from probability theory? Is because you really started out, with a particular model that coin tosses. There you can actually compute things, and you can actually you draw some pictures, and you see a shape appearing. You can just compute it from the formulas, and then afterwards you start thinking, wait, why does this happen? Why is it a Gaussian? And then it turns out that actually it's a Gaussian no matter what you started with, as long as you have something independent. Okay, so you develop your understanding by looking first at a simple model, then trying to understand what happens. And then actually one of the cool things is that the fluctuations are given by a normal distribution, and this is something that is universal, that we will see everywhere, right? I mean, to be honest, let me say a little confession here. When I did my first course in probability theory, I saw the central limit theory. I thought this is a very uninteresting area, because you just take the generating function and you do some sort of expansion, and the proof is 2 lines, and I don't see the point of of course I was wrong, because even though the proof is extremely simple, the result is amazing. Right? That you get a Gaussian is amazing. You get a Gaussian independent of the distribution. This is one of the really first year math, but extremely beautiful. Right? And this, you know, so I really underappreciate it. So I stayed away from probability to only realize later that I was stupid, and now I really like probability, and it will be a very probabilistic course. So I wish somebody would have smacked me on the head when I was a kid. But anyway, but this is so what we're going to do in this course is a little similar. And we go to the Aztec Diamonds, the coin tosses. We see pictures appearing, and then we want to understand these pictures. What is happening? And there is just a principle of statistical mechanics. When the system is very large, you will get actual fluctuations that maybe are not Gaussian as in the CLT, because the systems will actually be correlated. But you will get new types of laws that are just as beautiful as the Gaussian, and you will see everywhere in nature. Okay, so that's sort of the point. Okay, so that's a little bit the point. Okay, so now I want to discuss very quickly a different example of this phenomenon that was very attractive, and actually was, and I have a point of that, even though we will study tilings, I want to say a few words about a different area, an area that I also have worked in, and actually was very important also for the methods that I will see in this course, and that's random matrix theory. Because that will give you also an opportunity to give me my second confession today. Anyway, so let's look at a model that is rather simple to define. Let's look at Hermitian matrices, n times n, Hermitian matrices, and let's take them random. Okay, and we take them random. Okay, it's an Hermitian matrix, so we have a symmetry MJI. Oh yeah, you don't see that, right? The third property. MJI is MJI bar, but we have sort of the arbitrary angular part of the matrix to choose. And let's take those all IID, all the entries that I can choose to be IID, let's choose them IID. And let's take them complex Gaussians with a variance 1 over n, where n is the size of the matrix, right? So really I'm going to take a n times n matrix, and I'm going to fill them here with numbers. On the diagonal, I will just take them real normals, and on the arbitrary angle I'll take them complex normals, and these are of course fixed by symmetry. And then I will typically think that n is large, and I want to know what happens with the eigenvalues. Okay? Okay, so I'm going to take the eigenvalues of a Hermitian matrix. That means that I get, so I get a real line, you get a bunch of points. Right? So these are the eigenvalues, lambda 1, lambda 2, lambda. Okay? And these eigenvalues will not be IID, they will really be correlated. And let's just do something here. Let's just take a matrix, take such a matrix for n. So n here, n equals 40. Let's take a 40 by 40 Hermitian matrix. In this way, let's compute the eigenvalues, and let's see where they are distributed. Where are they? So let's plot a histogram given the configuration of eigenvalues. Let's give a histogram of where they are. Okay, and when n is 40, it's already large, but you don't really see so much. It looks a little chaotic, but when you start increasing n, you will see here that there is a nice shape appearing, and when n is 5,000, you really see a very beautiful statement. Namely, that the eigenvalues will be distributed they will all be on the interval minus 2 to 2, and they will have a density that is given by this, the semicircle law. Okay? There is really a semicircle that gives that. Okay? Now, if you ever went to, if you have been through some course or something about matrix theory, this is something very well known. If you haven't seen it, it's a little surprising. But it's sort of the same thing that as I saw with the Aztec Diamond, the tilings. When things go large, there is actually structure is emerging. Okay? So here also we see a semicircle law. So this is really a famous result around the matrix theory. It might be good to remind yourself of that, and it's not so important now. In the course, we will not look so much about random matrices, mostly about tilings, but it's a nice result to know that actually if you look at the number of eigenvalues in a number in an interval E, this is given by the integral of the semicircle over E. And the convergence to this is very fast, actually. Okay? Now we know very well why this happens. Okay? So around the matrix theory, we can actually compute, okay? I mean, I gave you a distribution on the entries of the matrix, but what you can actually do is you can compute explicitly the eigenvalue, the distribution of the eigenvalues, okay? And I will not say you how to do it. It's a very beautiful result, and it's surely highly non-trivial. But the eigenvalues, they have a joint probability distribution function that is written over there, okay? And what is interesting about this distribution function, because the shape of this will be something that we will also see in tilings. It has basically two terms. One term is the product of lambda I minus lambda j squared, and then there is a product over Gaussians, okay? So that's just, okay, don't ask me now how I did it, it's just something you can compute, okay? It's a beautiful theorem actually, Wiles integration theorem. So it's a deep result, okay? But let's just assume that this result is here. What does it tell us? Well, the first term is a repulsion term. The probability distribution function is zero. It vanishes when two eigenvalues are actually close. Okay? So what it means is that the probability of finding eigenvalues are close to each other is very small. Eigenvalues tend to repel each other. Okay? So they want to be as far as possible. On the other hand, there is also this Gaussian term. And when lambda is very large, this exponential is very small. So this will actually say, okay, you cannot be too far. So there is two forces. There's a confining force, and there is this repulsive force. And it turns out that there is a unique, nice equilibrium, and this equilibrium is indeed described by the semicircle. Okay, so this is a very beautiful result from random matrix theory. Okay. Now you can do another thing. You can look, okay, right? So this is sort of a law of large numbers. When we go to n to infinity, we see that there is a limiting configuration of eigenvalues. Now let's look at some fluctuations results. Okay. So I said that there is a very nice repulsion between the eigenvalues, which is below this. Okay. So now let's look a bit about something. Let's look at a point somewhere in the middle, x star. And let's zoom in, right? So when n goes to infinity, we have n points of minus 2 to 2. But now let's zoom in so that it's at such a scale that neighboring eigenvalues are of distance at order 1. Okay? So let's do that. Okay? And because of the repulsion, actually, all of them will be not so much clustering here. And now what I can ask is what is the probability of having no eigenvalues basically in an interval that is of that scale. Okay, so let's take an interval on the real line and let's ask when the rescale process has no eigenvalues there. So now there are two eigenvalues on the green line, but we ask for the probability that there are no eigenvalues. Okay. Now what you can show, and this is an expression that you don't have to understand now. I hope you will understand it after this course, and maybe also actually after today already something. The probability of having no eigenvalues of the matrix will actually converge to something that is a huge expression, and I will explain this expression today. It's the sum over k is 1 to infinity of minus 1 to the k, and then I have a k-fold integral, and then I have a determinant constructed out of a function of two variables, the sine kernel. It's so kxy, it's the sine pi over x minus y, pi over x minus y, and this is the expression you get. Okay. Now, one of the cool things about this expression is that it does not depend on x star. It doesn't matter where you were, you will always get this expression. Okay? So, not only that, if you would take a different type of random matrix model, you will also see this law. You will always see this limiting property. Okay? And this law, this is actually quite famous. This is what we call the Gauss-Meta distribution. And this is a distribution, a spacing distribution that you see all over in in math and in physics and in daily life. And this you should sort of think like this is like a law like a Gaussian. Okay? Gaussian is universal, you see it everywhere. This Gauss-Diameter theorem you also see. And this Gauss-Diameter distribution you also see everywhere. So there are two famous applications where you see it. Okay, one of them is from energy levels of heavy nuclei. If you have an atom that is very heavy, and you know that the energy levels of those are discrete, right? That you can jump from one to the other, and then you can emit radiation, and so on, right? So if you look at the energy field levels of an atom, this sort of completely describes what the properties of the atom. Then I claim that when the atom is very heavy, so when n is very large, when the atom is very heavy, so we have lots of, it's a large size atom, and the energy levels will have a spacing between them that looks very similar to this, okay? And which is one of the famous results in random matrix theory. Okay, so another nice application is if you look at the Riemann zeta function. I'm sure that most of you know this. The Riemann hypothesis is, of course, that the non-trivial zeros are all on the critical line. But if you would go up high on the critical line and you assume that it's true, yes, right, which we all do, of course, then the spacings between the zeros will have the same pattern as this. And it's extremely remarkable result that this that it's the case. But it's, you do numerical experiments, you see that it's true. And so this Gauss-Diameter theorem is really something that a distribution that you see all over. Maybe a little funny application is that you can also go to daily life. You can also go to a street here. Paris is probably not the best example, but let's take New York or some very long street. Look at the parks that are parked in the street, and then you look at the distances between the cars. And you plot a histogram of that, then you will see a similar picture. And the reason for that is that, cars, if you park, you don't want to be too close to each other. So there is a sort of distance, there is natural repulsion. And if you do the statistics, it actually matches pretty nicely. Usually when I'm outside of France, I usually give a talk and say, unless you are in Paris. So here I don't know if I can make the joke, but it's okay, yes. So there is a very different beta for Paris than I think, yes, for those who don't that count. Another very interesting distribution, one that we will see actually in the course, on tilings also, we will see this in tiling, is that you can ask yourself, like, okay, we have all these eigenvalues, what about the largest eigenvalue? What is the red dot here on the right? Do we have a bunch of eigenvalues, we know they will distribute to the to an interval, but what about the largest? And there's lots of applications for this actually. This is a very natural question that has lots of applications. And it turns out that the largest eigenvalue sticks to the bulk, as we say, will be around 2, and will have fluctuations of a particular order. Maybe I'll say a few words about this minus 2/3 also. And there will also be a distribution, a universal distribution for that. And it has sort of a similar form, and I just want to express again the form. That instead of the sine kernel, we get now something that is called the array kernel, which is built out of array functions. I don't know if you know special functions, you will recognize the array function. If you don't, then I will say a few words about that when the time comes. So no worries about that. But that's also a very beautiful distribution found only 30 years ago, and it's really one of the really a modern, like a similar thing as a Gaussian. Now I want you to take 3 aspects of this random matrix theory, because we will not speak so much about random matrices, but there were 2 types of objects that we looked at. Counting statistics, we counted the number of eigenvalues in a particular interval. We looked at gap probabilities, that there are no eigenvalues. And the largest eigenvalue is also a gap probability, but then for an infinite interval. And also that the shape of these distributions, they have a very strange form. This looks very complicated, okay? And I will say a few words about that actually. It's the fact that they are determinant point processes. So I will I will speak about that later. Okay, so now let me get back to the item to the Aztec Diamond. Okay, so why? And I'll also tell a little bit why I care about random matrix theory also. Okay, so let's go back to the Aztec Diamond. So what type of questions are we going to see? So one thing that we're going to look at is that if we take a very large Aztec Diamond and we look somewhere in the middle, just as I did with the eigenvalues of a random matrix, I can just sort of zoom in the middle, scale that everything is of order 1, and ask, what is this? What is happening here? What are the gap probabilities? What is this process? Right? Like we have the eigenvalues for the random matrices. We have the sign kernel appearing. I mean, what is happening here? Can we describe it? And I will do this in lecture 3, I think. Yes, I will describe these. And actually, what will happen is that in the limit you will get a tiling of the full plane, and it has some interesting properties. So that's one thing that I will go to do. Another interesting case, another thing that I will do also in lecture 3, is that I will look basically on this picture. I'll look at the interface between the frozen and disordered region, and then what you will see if you zoom in there. Again, I will explain why we get these scaling exponents also later. There's sort of a top path, right? There is a top path here that you will see. Okay, and you want to know what is the law of this path. Okay, so we're gonna look at that. And maybe I can already say that if you would sort of cut this path at a certain particular point, right? So you cut the Aztec Diamond in the middle, and there is somewhere a point where the last path is. What we will see is actually the fluctuation of this path. I mean, it will be basically near the circle, but the fluctuations of that point are the same as the eigenvalue, largest eigenvalue of GUA matrix. It will be the Tracy-Witten distribution. So that's the first connection, and another illustration that this Tracy-Witten distribution is universal. You see it also here. But we will say more about this. We will actually characterize sort of the process here. It will be done in lecture 3. Okay, so now another interesting thing, especially because I already spoke about random matrix theory. I mean, why speak about random matrix theory? And why you want to go to talk about tilings? Well, I mean, actually, I think the tilings are somehow the next level up. Random matrix theory is contained in tilings. Okay, so it's actually it's just a special case. So what you would do is if you look at where the circle touches the boundary, I would zoom in here, right? That I have a long strings of green tiles and then a long string of blue tiles, and then there is one yellow tile here, which could also be a red, and then another. You look at those, and now I'm going to put points at these tiles like that. So this gives me a point process. So this is also a way of illustrative of what we will do. We will look at the tilings as a point process by introducing points in this way, actually. But I will speak more about it in the next lecture. And then you can ask yourself, what happens? What is the distribution of these points when n goes to infinity? And it turns out, right? So again, I will take this. Just let's forget about everything. Let's just look at the lowest one. I look at the first level, then there is 1 point. Second level, there is a second point, 2 points, and then it's 3 points. And because of the combinatorics, everything, they are interlacing. So it's an interlacing structure of points that you get. And you can ask yourself what happens with the distribution of those points. And it turns out that these are the same in the limit as eigenvalues of random matrices, which is a remarkable surprise. So what you can do is you can look at let's take our mission matrix, look at all the eigenvalues, then take corners of this matrix. Yes, we take submatrices, like nested submatrices, and then we look at all the eigenvalues also of the submatrices. There is a result. If you have a mission matrix, you look at a submatrix, then the eigenvalues of the submatrix in the bigger matrix, they interlace. They have the same kind of structure as what happens, and what turns out is that in the end, you get the same distribution. So now, I go very fast on this statement, but I just want to make one point. Random matrices are contained in random tilings. Yeah, okay. So this is good. So we actually go one step further. It's a two-dimensional model. It's discrete. It has random matrix limits in there as well. Another thing that I want to prove, and I will actually spend a separate lecture on that with a nice method, is about limit shapes and fluctuations. So what you can do is that you can actually, with a given a tiling, there's always a nice way of making a 3D picture out of that, and I already did that before, right? And that's with the lozenge tilings. I said you can see it in a three-dimensional way. With the Aztec Diamond, you can also associate a three-dimensional. You can suffuse three-dimensional. You can introduce a height function. So, in the following way, you can define. First we draw again the points on the yellow and the red tiles. Okay. And then I'm going to define a function, a height function, that counts just the number of points that are at the right at the point that I'm looking at. Okay? So I filled out this array here, right? So in the left corner, I just count the number of points directly to the right. At the top it's 5. In the next one, I only have 4 equal to that are to the right, and 3, 2, 2, 1. Okay, and then I filled this matrix, okay? And this gives you a way of assigning a height function to the Aztec Diamond. I hope the diamond people don't shoot me, because this is usually not the way you introduce the height function, but it's an equivalent way, and it's a nice way for the perspective that I usually take. And what happens is that if you look, so you will get basically a random surface, yeah, right? So because here it's really like it's a height function. So here the height is 1, 1, 1. So you look on top of it, you see the height is 1, 1. When you look on the side, you see a nice random surface appearing. And what you can show is that the height function indeed converges this limit surface. It's a random surface, right? Because the tiling is random, the surface is random. When I goes to infinity, this height function will actually converge to a limit shape. Right? And not only that, the fluctuations around this limit shape are something that is called the Gaussian free field, which is a fundamental object in conformal field theory. So this is a very nice object that you see in these models. And we will actually spend, I plan to spend at least one of the later lectures fully on that, trying to prove that universality of that. And okay, so I hope I gave you an overview of the type of results. I don't know, either it was all trivial or it was ununderstandable. One of the two, I don't know. I hope at least this is the type of things that I want to prove in this course, and this is what the course will all be about. So just to say what I will start talking about, and today I will start talking about determinantal point processes, Chaire processes. No, actually not. I will speak not today about Chaire processes, but determinantal point processes, to put everything in a framework that all this process that all the randomness that we will consider in this course will be in the determinantal situation. We'll do this asymptotic analysis, as I said. We'll also see something called the shuffling algorithm, put some dynamics on these pictures. But everything will be from an analytic perspective. So this is a little bit what the content of the course. So maybe it's not only important to say what I will do, but what I will not do. So please don't, so you cannot tell me when are you finally talking about Castellan's theory. I will not speak about that. I will not speak about anything outside determinantal point processes. There's a lot of representation theory that's also very beautiful. I will not speak about that here. There's lots of things I will not speak about. Okay, so I will really start on determinantal point processes and stay in that class. Okay, so that's what I want to do. So this is the overview of what I propose. So the first 4 lectures I think I really should talk about. So I sort of fix those. Today, determinantal point process, we'll go to Chaire processes, LGV and a meta theorem. Lecture 3, I will study, answer these questions that I posed today. Lecture 4, I will go a little in some shuffling algorithm and some dynamics, and do an algebraic formalism there, which I think is very beautiful. And then 5, 6, and 7, I want to go to a little modern topics that go a bit further. So I propose now that I have a proposal there that something that I like very much, doubly periodic weights. This is a particular weights where the pictures become more exciting, and new types of randomness that we want to study. So this is something recent. I will speak about the Gaussian free field, and I will do this also in a different, from a different perspective, my own perspective on the area. And then in lecture 7, I intend to speak about some nice things that somebody was working on Panové transcendence. So I'm happy I kind of in the end also say something about critical phenomena in random tilings. When disordered regions undergo sort of topological transitions, you will actually see that the partition function will go through Panové solutions. And this is something that I want to show. I'm also open for suggestions. There are many other types of things that want to talk about. So especially in the last lectures, if there is a strong desire from the audience to talk about a particular aspect that I did not put on here, then I'm definitely open for suggestions. So yes, so that's sort of the plan for this course. Okay. Any questions? No? No, very good. Okay, so then let's start. Okay, so let's start. So I guess we will have a break in half an hour, right?
Yeah.
Yeah, perfect. Yeah, I can put here, right? I should first turn off the presentation before we. Okay, the framework where all these models live, both random matrices but also these random tilings that I will discuss, is actually the theory of determinantal point processes. Okay, so that's something that I want to talk about today. Okay, so today will just be about determinantal point processes, and it's quite a beautiful theory, and it can be quite technical very quickly, but it's slightly easier if you are working with discrete processes. So that's what I will do today. I will mainly work today about how to set up discrete determinantal point processes, because there the structures are a little easier. Then once you understand that, you understand what you need to do, and then you just assume that you can do the formalism for the continuous determinantal point process. And if you really insist on it, I have a detailed discussion on that in the lecture notes. Okay, so I will just very quickly go through that. So determinantal point processes. Okay, so first of all, what is a process? Point process. Okay, so let me first start. So that's the title for today. So let me first say what are discrete, and I will say now, but I will drop discretes very soon because I will always assume it. Simple point processes. Right, so we can think about these eigenvalues. Well, then actually it's continuous, but you can also look at the points that I draw on the tiles. They give you a discrete point process. Okay, so it's just going to be a space X. This is where the points live. This is just going to be discrete, right? And for now, actually, you could just think that this is just a finite set. But if it's not to be a finite set, that's totally fine for today to think about. But if not, you could take it a little larger. You could also take it from a sort of a metric space, but no accumulation points. So what it means, metric space, but let's say that bounded. If a set is bounded, then it also implies that it's finite. Okay, so there are no accumulation points. That's basic. That's important. So, well, whatever you think. I mean, you can think about X as a subset of Z, or Z to the D, or anything. That's also okay. Or maybe some graph. Doesn't matter. Okay. Then okay. So then a point process. Do I write big enough, by the way? No. So a point process, so a simple point process is, so it's just a collection of points in my space X. That's it, right? So it's just a random collection of points. Well, number of points in our X is just a subset of X. So it's basically just a random subset of X. So this is a probability measure on 2 to the X. Okay? And I say simple point process because points cannot occupy at the same, you cannot have 2 points at the same location. Otherwise you cannot just say it's a subset of X. Okay? So there are no points at the same location. Points are never at the same location. Now it's actually a Borel probability measure. We should be a little bit careful here because if X is discrete, or X is n, then 2 to the X could still be quite a complicated space. So we should say a little bit about topology, but let's skip. I mean, the topology you can put on it is the one that is generated by bounded sets. I will not say too much about that. Just look at the details in the lecture notes. In the lecture notes, I'm precise. Okay. Very good. Now we will look at, if you have a point process and you want to study a point process, there is a number of objects that are very natural, and we already saw a few of those in the slides. One thing you would like to know about the point process is maybe how many points are there in a certain interval. Okay, so that's the first natural statistic. So if you have a bounded set, or maybe it doesn't have to be bounded. The counting statistic, this is something that we will use. The counting statistic associated NA is defined as well, just NA is just the number of points, right? The number of points in A with our random configuration X. X will be my random configuration. So it's just the sum over all the random set X, where you have the chi. Chi will be my notation for characteristic function of the set of this. Okay, so that's just you just count the number of points in the set, and that's of course a random variable. Okay. So so this is the characteristic function. Just want to say this is just. I mean, this is my notation. I will use this frequently. So let me just write it for once out, so we know what it is. And zero, if it's not important. Okay, very good. Okay, so okay, it's a very natural thing to test, and not only that, it's actually also something that completely determines the process. Okay, and that's just my next definition. Although we have to, this is called the finite dimensional distributions. So let m be an integer, a1 to am, let's take these bounded sets, and k1 to km, these are integers, or let's include 0. I never know in which country 0 means you include it or you exclude it. I include it now. Okay, that's my convention. This depends on country to country. Then we define and set just the p m a1 to am to m k1 to km. This is just, these are numbers, and they are just the probabilities that the set A1 has K1 points and A of AM has Km points. Yes? Okay. So these are what we call just counting the number of points in the different sets. And these are natural type of statistics that you want to understand from a point process. And not only are they natural, they're also sufficient. If you know all what the distribution of these things are, if you know the finite dimensional distribution, they uniquely characterize. So let me just put a little theorem, just a remark maybe. They uniquely characterize the point process. So everything is contained in these numbers. So that's one thing. Another thing that that we will use frequently. Remember, there was this gap probability. So there's actually maybe a slight generalization of this, but it's a notion that covers them both. If I have a point process P, I can sort of look at observables of the point process, and they're defined as follows. So for any G, this is now with bounded support. We define phi of G as the product over all values of 1 plus G over all the points in our random configuration, and then we take the expectation. Okay, so this is a nice observable, as you should sort of think. This is a very natural thing to do. If you basically know all the phi G's for all given G's, then you basically know the point process. Okay. And not only that, there are some special cases. So there's some nice special cases. Maybe you think, why do you write 1 plus G of x and not just G of x? I have good reasons for that are not clear now at the moment, but we'll see that our point processes could have infinitely many points, and then you take infinite products, and you have to be a little careful what you mean with that. Okay, so this is better to write it like that. Okay, so an example is, for example, if G of x is like this, let's take an I t of an f of x minus 1, so I get rid of my 1 again in the first example. Maybe not the pedagogically smartest example, but that's I hope you don't mind. Then this phi of G, right? So that's the phi of e to the it of f of x minus 1. This is just the expectation of e to the it of the sum of f of x, where x is in my random configuration, right? So I hope it's clear that this x is not the space, right? This is a random configuration, right? So there's an x and then there's a bold-faced x, right? So I hope it's clear. Right, and this looks a little bit like a Fourier transform of what we call a linear statistic. Okay, so that's also an interesting object. This is the Fourier transform of the sum of f of x j. Okay, and this is called a linear statistic. All right, so that's these are nice things to actually study. When I come to the lecture on the Gaussian free field, this will actually be the starting point of the lecture. Another interesting example is when g of x is minus the characteristic function of a set x, of a set A. Okay, let's take A, a bounded set, and we take minus the characteristic function. Yes? So what will happen then? Alright, so what will happen then? Well, then the product of x in x of 1 plus g of x, what is it? Well, this one is either minus 1 or 0, right? Depending if x is in the space of A. So now I take a product over points in my configuration. So this is going to be 0 if there is a configuration point in my configuration that is also an A, and it's 1 if it's not there. Right? So this is 0 if the intersection here is non-empty, and it's 1 if the intersection is empty. Yeah. And what does it mean? Well, if I then look what happens with the expectation, well, the expectation is just 1 on the event that the configuration has no points in A, so that's the probability of having no points. This is the probability of having no points in A. And this is was something, for example, that this Tracy-Whitten distribution and the Gaudium-Mated distribution, these universal distributions, they were of this form, right? They were gap probabilities. They were probabilities having no eigenvalues. So this is an important example. Okay. Now let's take another example, and then maybe continue. There's a nice example. Is that if g of x is z to the x, z to the chi of A minus 1. Again, minus 1. But I told you that I only write 1 because I want to make sure that things converge later and so on. So that's just more practical. What happens then? Well, then, again, we get just e of z to the chi of A, right? So, sorry. The product over x of z to the chi A of x. Well, every time, I take product, every time I have a point in my configuration that is also an A, it gives me a factor z. And if it's not in my set, it gives me a factor 1. So what is this? This is just the expected number, the expected value of z to the n of A. The number of points, obviously. So this is actually maybe this is what we can call the z transform for the counting statistic. Okay, so it says okay, so these were some important things. So we really want to think about what happens with these things, because they contain quantities that we care about. Okay, any questions about this? Okay, well, if not, then the next step here is to go to look at this expression and rewrite it a little bit. Okay. for that, I need to have a little notation again. Let me first start with a little notation. I'm sorry that maybe today is quite a lot of sort of definitions and so on, but okay, that's how it, I have to set up the world we're working in, so that's it. So if I have a set A, so let's take a set A, and now look at A of m. M is an integer. Then A of m consists of all tuples x1 to xm. Yeah. That are in A to the m. So all these points are elements of A, but they have no duplicates. So j different from k implies also that xj is different from xk. Okay, so that's just real different, like m tuples in A, and they're all different. Okay, that's sort of important. Okay, I will need this now, because what I'm going to do is I'm going to expand now this product here. Okay, so maybe I should I'm going to have a theorem that for any G with finite support, we will drop this finite support later, but like for now we keep it there. I can write the phi G, I can expand it, and I can write it in the following form. It's 1 plus the sum from m is 1 to infinity, 1 over m factorial times the sum of x1 to xm in this space. Yes? I look at all tuples, I sum over all m tuples in my space, and the points are all different. Of gx1 to g of xm times rho m of x1 to xm, and rho m of x1 to xm is the probability that x1 to xm is actually is contained, the points contained in my random configuration. Okay? Right, so is it clear what is written? Yeah. So my phi of g has the series expansion. Okay. Note that this is an infinite series, so you may have to wonder, and we will wonder about it, but first we need coffee. We will wonder about this in a minute, because you have to sort of wonder about the convergence. However, these points are all different, and G has finite support. So if there are, if M is larger than the number of points in G, then this is automatically 0. So it's actually will be cut off. Okay, so we don't have to worry about that. We will have to worry later. Yes. Now I can give a proof of this statement. However, there is a proof in the lecture notes, and the proof is a little boring, because the only thing you do is you write out this product and you organize things. And those of you that know me know that I'm very bad in organizing things. So I will, unless you insist on doing it, I will write out a proof. But the proof is really that you write out this product, and you have a product over all the terms. Then, in each product you can choose either 1 or G, right? So now let's just take a bunch of 1s and then a bunch of G's. Let's take m of those G's, which gives you those, and the rest are 1s, and so it's just a combinatorial exercise. It's not very difficult, and there is a proof in the notes, I'm not going to waste my time and energy on that, okay? But it's very important. Because these guys here, these things here, they are called the correlation function. So this is called the endpoint correlation function. Okay. Oh, yeah, well, that was a little too enthusiastic. These are the endpoint correlation functions. Okay? And these are very important objects when it comes to point processes. Now note that the 5 Gs, we already saw that, they contain everything you want to know about the point process, right? If you know the 5G for all of the Gs, then you know the point process. And now we also have the fact that we have these, instead of 5 Gs, we have got these rho m's. Well, the rho m's, they actually determine all of the 5 Gs. So the rho m's, they contain all the information of the point process, okay? So the rho m's are really things you want to control. So now comes my definition of a determinantal point process. Okay. A point process is called determinantal if and only if there exists a function of two variables, both in my state space, right? So let's take it complex, such that the rho mx1 to xm, this is of course for all of the correlation functions, this is a determinant out of this, okay? No. Yes? So that's the definition of a point process. Right? So this is, note also that this was the probability that x1 to xm is in my space, is in my configuration. Okay, and this is a determinantal form. Okay, so we have m points, and then we have an m times n matrix, right? So we have really this matrix. I mean, you just write a little bit just to give you make sure you really get it. It's x1 to x2 to k of x1 to xm. And we go all the way to xm to xm, right? We form this m times n matrix, and then we take a determinant of that, and that should be that's the determinantal point process. Now, I don't know if this is the first time you see a determinantal point process, you think like, what's going on? I mean, this is not, this sounds, I'll claim that this is very useful. And then you say, yes, I can imagine that this is very useful, but no process is going to be of that very beautiful form. And here we have to be very grateful for nature or God or whatever, that many processes actually satisfy this, which is a bit of a surprise. Okay? And the random matrices and the tilings that I gave, they all have this structure. It's just a piece of luck. Definitely not true that all of them, but having this form, I claim, is extremely useful. And for one thing, it's very useful. We know that this kernel is a kernel of a function of two variables. Right? I started with a point process, could have infinite points, could have many points, and then okay, if I know the finite dimensional distributions, then I know my point process. But the finite dimensional process, okay, then I need to count number of points in any configuration of sets. Or I compute the phi of G, and G could be anything. These are very abstract objects. Right? But now I'm claiming that I also said the endpoint correlation functions, they determine everything in the point process. Okay, but then you need to know all the collection of the correlation functions. But if we have this form, And everything is encoded in a function of two variables. So the only thing we need to understand about the point process is this function and its properties. And then we can deduce all these laws that we some of them that I put on the screen. They should be hidden, they are hidden in that function of two variables. So this is a rich family, this is a rich function, and we need to study that. It's 15:30, so we can maybe have a question. Yes.
So if I give you a function k, does there exist a point process with any k?
Very good question. So now, right, so this is a very good question. So there are two different games you want to play. You start with a point process. You need to find your k. How do you find k? Okay, I will answer that question for tilings. Then you can do the other question, which is also very exciting, and I will do that today. Suppose I give you a k, is it a correlation function or is it another point process? And are there special k's that sort of generate these point processes? And the answer is will be given after the coffee. I can already tell you that I had these gap probabilities, the Tracy-Witham and the Gauss-Diameter theorem. They were exactly of this form. Right? So maybe I'll just recall them. K of xy is the sine of pi x minus y. X minus y, this was one of them. Okay, here everything is discrete, so it's not continuous. I didn't talk about continuous here, so this was really continuous because we're random matrices. So strictly speaking, it's not really an example of this. And I will also, after coffee, explain why actually this definition doesn't really work in the continuous case. It works, but you have to be a little bit careful. Correlation functions in continuous setting cannot be defined in this way. For the very simple reason that if it's a continuous distribution, having a given point in your distribution that the random variable is exactly that point is probability 0. So it doesn't make any sense. So you have to be a bit more careful. And I will just give a very brief, very straight to the point argument, not argument, just a sketch on how to think about it, because the actual definitions for a continuous process are a little annoying, and they are in the notes. So, coffee, or maybe more questions. Oh, okay, coffee. Okay, so let's continue our discussion. Let me quickly remind you very briefly what we did just before the break. We looked at the point process, simple point processes, and then we looked at this type of observables, right? So that's the phi of g. Then we expressed them, we did an expansion of that, to the definition of correlation functions that are then defined as the probability of the random configuration contains the points x1 to xm. And then we had a definition that says, okay, everything is determined by the correlation functions, and the point process is called determinantal of these correlation functions of this very, very special form. Okay. So, and then I got a question. What is this relation, this map between point processes and kernels? And basically the rest of a big part of the rest of today is devoted basically of that question. What is this map? So first of all, something that is important to note, and actually a little complicated sometimes, but it's very important to, okay, I'll make a few remarks. The kernel, you cannot speak about D, so actually we will say here also in this case that K is called, and now it's important, a correlation kernel. For the process. There is no such thing as the correlation kernel. Okay? Why not? Well, there is a little remark. We make some remarks. Well, one is that if K is a correlation kernel, and G is a function on X that is strictly positive, so let's just say anything actually, wait, 0, it just never takes the value 0, then Kg of xy, which is defined by K of xy of G of x over G of y, is also a correlation kernel for the same process. Is also a correlation kernel for the same process. Okay, so that's important. So that's actually that's something that this is not just this silly remark. And by the way, first, does everybody see that it's true? Because if you look at the determinant of the kernel, you would what this conjugation does is that you multiply by gxj and you divide by gxk. One of them is multiplying all the rows by gxj, right? And then we have dividing all the columns by gxk. So that's a conjugation, and that doesn't change the determinants. So it's a trivial thing to see. It's just the fact that it's just conjugation of the kernel. The determinant doesn't change. And okay, so there is no such thing as the kernel. It happens. You will see this in asymptotics that there's often these things going on. And one of the problems is that there is no canonical choice of the kernel somehow, right? And this is a little unsatisfying. So some kernels, there's a lot of kernels, I will speak about that later, which doesn't have to be, but sometimes, right? So sometimes, if you're lucky, we have kxy is kyx, right? So then there is it's self-adjoint, right? Or it's symmetric. So this is great actually if you have this property. We will actually answer your question in this way. And then there is a canonical choice. It's, you can just, if you change this by g, then you still, well actually it's still not completely canonical, but then you could easily destroy this. So a lot of processes that appear like they are not self-adjoint, they could still be equivalent to something self-adjoint by finding out these factors. But okay.
Maurice?
Yeah.
Is it unique up to this transformation, or could you have other things as well?
This is a question that I think everybody believes the answer is yes, it's unique up to this transformation. And I think in certain classes there are proofs, but I think in general, I'm not sure if it's true. I think that
it's like a gauge transformation, right?
It's like a gauge, yes. It's I wouldn't now, especially with the camera on, not give a definite answer to that. I think that in certain subclasses you can see that that's the only way to do things, but from a general perspective, I'm not 100% sure. Yes. Let's see. Right. Okay. Right. Okay, so there's also something important. Just let's do some simple computations. I mean, remind also that the row run of x, right? The first correlation function, the 1-point function, right? This was defined as the probability that x is contained in our random set, right? So it's the probability of having a point at the location x, right? That's a simple quantity that you like, and that's actually equal then to the determinant, but now it's in 1 times 1 determinant, so that's just kxx. Okay, so that's a nice statement. So this kernel, the diagonal kernel, basically gives you the probability of finding a point at a certain location in the discrete case. The row 2 of x, that's a function of 2 variables, let me call it x and y. So that's the probability of having an x and y, so a point at x and a point at y. It sounds like an interesting thing to compute, of course. What is the probability of having a point here and a point there? Well, you know, if you have independent points, that's just the product of probabilities, but now it's not. It's the determinant. It's the determinant of kxx, kxy, kyx times kyy. Yes? Okay, why on earth did I do this only in the last line? And this is kxx times kyy minus the kxy times the kyx. Okay? So it's a probability, so this having a probability of having a point here and a point there is given by this expression. Okay? Note that kxx is the probability of having a point at x. And this is also a probability of having a point at y. So this also equals the probability of having an x in x, right? Times the probability of having a point at y minus the kxy, kyx. Okay? So if the point process would be independent, you would just have just the product of the two. But now we have an extra term, and this shows they are correlated. And not only that, if you have the kxy is kyx bar, if it's symmetric, then this will be actually positive. So then, and there is a minus sign here, so it will be negative. So it's negatively correlated process. That's an important property. But of course you need this property. So it's self-adjoint. So that already tells you that self-adjoint is so special. Yes? Okay, very good. So these are some and of course you can compute further, right? The probability of having 3 points somewhere, it's going to be a larger determinant, blah, 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 and so on. You can do this. Maybe another remark that is maybe nice is that if you would count the numbers of the number of points in the set A, well, that's just the number of points in the set A is just the indicator on the sum of A. So actually, simple computation, I mean, I'll do this, is that this is just the probability that we have a point at x for any x in A, right? So we sum over all points in A. Okay, that's this. And the variance, and this is an important thing. I want you to remember this. Again, you can just compute this, right? So let me really show again here that this, right? This is the variance of what? The sum over x and A of chi of x here, right? So this is the indicator function for the random configuration over all A, right? So if you just compute what it is in terms of the correlation functions, there is a proof in the notes, and if I will do it, I will fill the board with determinants, which after my last linear algebra course, I hope never to do in public. So So let me not do it, just give you the answer. This is just going to be the sum over x in A of kxx minus the sum over x and y in A of kxy, kyx. This is sort of similar to this computation. But note that I did not make a mistake. I don't have a square here. It's really this guy. This is a computation you can do, and I don't want to do it here. Okay, it's in the notes. It's a simple computation. I just want to tell you that, and this will be something important for us. Yes, okay, very good. Okay, so let me say one more thing. Is that we have the correlation functions. They are all determinants in the determinable point process. Yes, that's what the definition was. But actually this means a little bit more because there is another theorem here that says that if K is the correlation kernel for a point process for a DPP, and let's take what? Yeah, so G is a function, so X, and G has finite support in X. Well, then the phi of G is going to be 1 plus the sum of m is 1 to infinity of 1 over m factorial times the sum of x1 to xm in x times g of x1 to g of xm times the determinant of this kxi times xj, and I and j run from 1 to m. So this is actually already a theorem. Why is the theorem? Because we just had a definition, right? Well, it's a theorem. It's very weak now, what I'm saying, but you know, you can just ignore. Here, first we said all the tuples have to be different. All the points in the tuple have to be different. I had a definition here. It was an M here, all the tuples, but now they can be the same. Why? Well, clearly when they are the same, this determinant is going to be 0. So that was a very simple theorem to prove, but it's yes. But something more is true. That's the more interesting thing. This actually equals the determinant of I plus gk. Okay? And the gk here, this is a matrix, right? So gk, this is a matrix. This goes from x times x to c, which is just defined as g of x, k of xy. Right? It's just a matrix where x and y are. So it's a matrix with indices in a discrete space, and it has this form. Okay. Okay. So here there is a little. Here I have to be a little careful here. I have to say a few things. So first of all, is it obvious that it's the case? Well, yes, because it's the first thing that you want to do if you want to prove this, and there is a proof in the notes again. You take again this sum. sum this over everything, but then you can put sort of the g into this determinant. Right, so you sum over that, you put the g's inside the determinant, and then you recognize that this is the von Koch form of the determinant. Okay. So if you G has finite support, so I can just think about restrict this to the support. I can see this as a finite matrix with indices in the support. It's a finite matrix, and I can take the determinant of that. When I do the determinant, I can start expanding. And every time you do, just expand your determinant in the usual way. Every time you have to make a choice. Do you take something from here or something from there? Right? If you take from the identity, then you remove actually some columns and rows from this guy, and that gives you a minor of that matrix. That's what it is. It's a very annoying computation to do, but it's not difficult. Okay? So this is actually, it's not just that for determinantal point process, not just is it true that the correlation functions are determinants, actually these observables are determinants themselves. Okay, so determinantal point processes is just business where they compute complicated determinants, right? So, and their properties. Okay? Now, I want to say a few things because I'm really tired of writing finite support all the time. And actually, and sometimes we really do not want finite support. We want something more general. But then you go to determinants of matrices that are infinite. And I don't know if you ever thought about this, but how do you define the determinant of an infinite matrix? Or in general, if you go to continuous determinantal point process, I'll just sketch a little bit in the end. How do you take determinant of operators? How do you do this? And this is a highly non-trivial business, actually. So I just want to say a few, very quick, I have actually in the notes, and this is totally unimportant, but I like it myself about this theory, so I included an appendix where I just discuss how to extend determinants to operators from a Chaire perspective, and I just want to say a few words about that. Because somehow it's important, otherwise we will speak a little bit in the air later. So we have to, how do you define this? And yes. Okay, let's go. Right. So what we do is that if you have a matrix, okay, if you have a, sorry, yes, no, let's see. Yes. So if you have a matrix that is now infinite, I'm going to extend the definition. I mean, if you look at the operators on L2 of X, okay, and you have an operator on that, and you want to study the determinant of the operator, or maybe 1 plus the operator, how do you do this? Well, it should be obvious how to define the determinant of a finite rank operator. Yes? If you have, or just a matrix. I mean, some of the operators only work on a finite dimensional subspace. So for those, the determinant should be obvious how to define. And then you go to a larger class of operators by introducing a topology, embedding your operators in a certain class of operators, and show that the determinant is continuous with respect to the topology, and then you extend it. That's sort of easy. And then, okay, that's an abstract definition, but you still have to show that all the properties that you think the determinants that they hold. So, for example, you would maybe want that the product of the determinant is the product of the eigenvalues, these kind of things. But you have to check that, okay? So let me just say that for the discrete case, again, the discrete case here is easier. If I have an operator, so let's just take R. R now is I want to not say write K because we want to apply this not with K but G times K. So let's do this with R. This is sort of so these are X times X matrices, and I'm going to define a norm on those, which I will call F. It's the maximum over the sum of K of XX, where X goes in the space, so the sum of the absolute value of the diagonal. Let me write this properly. It's the sum over K XX with X in the space, and the double sum over X and Y of KXY squared.
R, right?
R, yes. R, and then I take the square root of this. Yes. So this I call the norm of R. Okay. And as long as this norm is finite, I claim I can define the determinant of the operator, of the determinant of identity plus R. Okay. So I will now, so D then is the space of all R such that the F norm of R is finite. So, okay, so I claim that for these operators, I mean, note that if you have only, if R is such that most of the entries are 0, and it's just finally many are non-zero, then it's just basically a finite determinant, then it's no problem, then we don't see any issue. But if it's not, okay, then I claim that if at least these both numbers are both finite, right? So here I have the L1 norm on the diagonal and the L2 norm of the entries. If that is finite, then you can still define the determinant in a nice way. Okay. So there's a few nice properties. So one nice property, which is nice, which we will use for, is that actually this D is a Banach algebra, meaning that if A and B, no, R1 and R2, if these are in our algebra, this space, then also then R1 times R2 is in that space. And the norm of R1 times R2 is less or equal than R1 times R2. So, and this is all the F norm.
Why F norm? What does the letter F stand for?
Now I'm actually, I was actually wondering.
The second ingredient is the Frobenius norm, right?
Yeah, so I think that's.
This is sort of a modification of the Frobenius norm.
Let me take full responsibility. This might just be my only reason when I wrote this. I don't think this is a universally accepted way. I'm actually wondering when I was writing it down, what was the F again? So I think it might just be that. I mean, this algebra, this does have a name, so maybe we might have a better letter than F. This is called the von Koch, same guy from the determinant, Ries. This is the von Koch Ries algebra. and this is a very nice property to have. Okay, and not only that, there's another. It's like the finite rank. So that the finite rank. There's another two. The finite rank are dense in this case. So the finite rank operators, right, are dense in this space. Okay. So, okay, and yes, okay. So that's it. So with that definition, with that, I can basically state a few new definitions. So if you have a R in the Foucault algebra, then you can say that then the trace of R is going to be defined as the sum of Rxx, the values on the diagonal, just as you would define the trace for a matrix. And that's one. And two, the determinant of the identity plus R is going to be sum of 1 plus the sum of k is 1 to infinity of 1 over m. I usually use m here, so it should be consistent, times the sum over x1 to xm in my space of the determinant of kxy, kxj. I and j run from 1 to m. Okay, and okay, so at this point, I really write the trace as I want, and the determinant, I just write the same expression as I had before, and I just don't care about the infinity. I just make it now, but now it's not finite anymore. The sum is not finite. It really contains everything. So we have actually this is not automatically well defined, and so let me just write a little theorem. It is well defined and convergent, and we have the following properties. Okay, so maybe I should not be too fast and give you some time to write also. By the way, all the notes are already online, so if you want to check something. So the theorem is that the trace and the determinant are well defined. And some properties, so we have some properties, well, we just take the trace of R plus R2. If I have two operators, then that's just the trace of R1 plus the trace of R2. Of course, the trace should be linear, and it's of course the case here. This is not a very difficult statement, but it's still something you actually have to verify, right? Because you know that for matrices it's true, but now you define things by basically, let me first, because I didn't really, sorry, let me do this, let me do first the statement. The maps are to the trace of R, and are to the determinant of either plus R. They are Lipschitz continuous. So this one is Lipschitz continuous. And so this one is locally Lipschitz continuous. Okay, is it clear what that means? No. So what it means is the following, that if I have a determinant, if I have two operators, R, and I look at the determinant of identity minus R2, this is less or equal than a constant times R1 minus R2 with F. Okay? this is what it would mean, that there is a constant such that the difference between these two determinants is bounded by the norm of the distance. Difference times the constant. Then it would be globally Lipschitz. And now this constant may depend on R1. So it's locally, it just means that there is this constant, like in the neighborhood of your point R1, there is a constant, but that constant depends on your point. But in any case, it means it's continuous. Okay? So the trace and the determinant are continuous with respect to this norm, so you can extend it. And now should come the lemma, and then the statement is that it's continuous, and if you take the limit, you really can sort of pass the limit through to the sum. This is really the expression you get. And then I also have this statement that it really behaves like a determinant should. Okay, so there is another. And we have the properties 1. Trace of R1 plus the trace of R2 is the trace of R1 plus R2. This is very important, of course. I mean, clearly it should hold, but you have to verify it. Second, the determinant of 1 plus R1 plus R2 plus R1 times R2 equals the determinant of identity plus R1 times the determinant of identity plus R2. It's just saying that the determinant of A times B is the product of the determinants, right? Determinants respect products. It's just that we have not the product determinant of A, but of R, but of 1 plus R. That's just what it's saying. And another result, and this is important, identity plus R1 times R2 equals the determinant of identity plus R2 times R1. Right? So you can switch the order. That's a well-known result, but it's all valid. So you can just really think about them as determinants. Okay, so we can take determinants of operators, and the whole statement is that the determinantal point processes, if you look at these observables, which basically contain everything, gap probabilities, counting statistics, or linear statistics, you're actually computing determinants of operators. Good. Okay. So very good. Very good. Yes. Very good. Okay. So I want to go to answering your questions. So. Good. I want to say one thing here, and this is for let me not say that. Sorry, I will come to the proof. I will say that. Sorry. There is a nice. So everything I said so far can be extended to the continuous setting. There's one principle that is very nice, which is specific for discrete setting. Okay? And that's something that is a very beautiful statement, which is particle whole duality. Okay? So yes.
Is this algebra invariant under conjugation?
Is this algebra invariant under conjugation? No.
The K is not.
Yeah, so the K is not really, yes, so no, this remains an issue, this is not reserved. So you can have that K is, that the correlation kernel K, K sits in the weak algebra, but then you start doing this, take another one, take another gauge, and then you're outside. So you have to be a little careful. Because, why can you be outside? because it's not rxy, ryx, then it would cancel, but now it doesn't cancel. So, but in the determinant, it doesn't matter. So this is always a little pain. So to define the gap probability, if it's not self-adjoint, you typically have to bring in the right gauge to make sure that the operator exists and that you can define the determinant, and once you have done that, you can kick it out. So that's a technical issue that that you have to live with. I'm sorry. Yeah. Okay, so the particle hole duality. So there is that's a very nice identity, which is the following. So let me, before I come to the statement, let me just say what's happening. So we are looking at a point process, right? So let's say that the process lives on Z, right? And now we have a bunch of random points. Here's a point, here's a point, and here's a point. And then I can study the point process there, right? But there's a completely dual picture, right? Because I can also look at the places that are not occupied, right? I can also circle with another color the other particles. And then I can say, okay, but then I just switch, you know, these are not the particles, these are the particles, and these are the holes. Right? So there is a complementary, just go to the complement of it. And then there is you can look at the process of the particles or the process of the holes. These are equivalent, clearly, but they are different. And there is a very nice statement that says, right, so if K is the correlation kernel for the process for a DPP, like a particle process. For a particle process, right? So let me write it like this all the way on X. Then 1 minus K is a correlation kernel for the whole process. Yeah, right? I mean the whole process. And that's a very cool duality. If you and people do this happens a lot in tilings, for example. You know, you are working with one point process, and then you think, this is annoying. I have to go to the other ones, and then you go to the complement. Okay, that's easy. You go just from K to 1 minus K. So this is and the proof of this is actually very simple. But let me not, maybe let me not do it. You just compute the probability of a gap. You know, the points, the holes, these are just the gap probability. And then you write it into this determinant. You spit out the determinant, and out comes exactly the determinant that you want. Okay, so I will not do this. It's an easy proof. You can read it in the notes, but it's a very useful concept. Okay. So now I can come to the final question. So the rest of the time I will just spend on doing examples. Okay, let's now. This is all general theory for let's do examples. Of the determinant point process. And okay, so when is a, let's stay in the class that kxy equals, kxy equals kyx bar. So self-adjoint. That's sort of a useful self-adjoint kernels, K that are self-adjoint. Not all kernels that we will see are self-adjoint, or symmetric, I mean Hermitian. Self-adjoint, I have to be a little careful. I will actually use it in a minute. But many are. So for random matrix theory for the GUE, it is actually. So many cases it's true, but definitely not always. Okay, but it's an important class of examples. Now, what this definition means here, like if the correlation functions, right? These are the correlation functions. If these are positive, right? Because there's a probability that that a certain configuration is in our set, right? All that x1 to xm are in our configuration. So these are actually probabilities. So these are positive, right? So if I have a function kxy, so actually a matrix, right, indexed by x and y, and I wonder now, okay, when is this k now the correlation curve of a point process? The first thing that I need to show is that, okay, all the minors, all the principal minors need to be non-negative, right? They need to be at least, not zero, not negative, right? So that's one thing, right? But we also have the particle Hall duality, saying that, okay, that also means that if I look at 1 minus the kernel, it should also be have positive minors, or non-negative minors. So if I start with a matrix, and we say that this is now so that's a theorem actually, so that's a big theorem. If k, so this is now a matrix, right? So kxy is acts as a self-adjoint operator on L2 of x, then k is the correlation kernel for a determinantal point process if and only if k is self-adjoint, right? It's totally it's a positive non-negative definite matrix that has to, because we have all principal minors need to be positive and non-negative. Sorry. So that means that the spectrum should be positive, right? But also for 1 minus k, the spectrum should be positive. So it's in between. And this is a beautiful theorem, I think, in my opinion. So any self-adjoint operator that has a spectrum in 0 to 1 is the actual correlation kernel for a determinantal point process. So you can start building many examples. And this answers your question, I think. Now, the general question is not entirely obvious. I mean, in this class of self-adjoint, it's sort of, this is decisive. Okay, that's a beautiful theorem. And I have how on earth do you prove such a thing, right? Because I have just a function. How do I construct a point process out of this operator, right? And okay, the proof is a little is in the notes. But let me say a few words about this. It's actually not so hard if you know general theory of point processes, because what you construct out of, so if and only if, right? So if you have a point process and it's self-adjoint, then k needs to be in that's sort of the easy direction, but starting from the operator to construct a point process, that's the difficult one. What you do is you construct a set of functions that should be the finite dimensional distributions, okay? And then you show by Kolmogorov's theorem that there exists a process with those finite dimensional distributions. Okay, there are sort of consistency relations for finite dimensional distributions that I didn't talk about, But there's certain, if you start with this, with a set of functions, and you ask when are they the finite dimensional distributions for a point process, that question has to be answered by Kolmogorov. So we only have to construct these finite dimensional distributions. And how do we do that? Well, we just construct this, right? So this is a proof. It's A1, AM, K1, to Km. I construct those in this way. It's 2 pi I over m. Here is the contour integral. I will use the I guess I'm speaking for an audience of mathematicians, so don't shoot me. I actually don't really mind the physics definition of the integral, to put the dc not in the end, but doing directly after the integral, especially when there are multiple integrals. I like this convention, so I will do this sometimes. Please don't object. And then here there is the determinant of identity plus z1 to what? To chi1 of a1 times zm to chi-m of am minus the identity times k. And that's it. Oh yeah, over times z1 to the k1 to zm to the k, and I think it's plus 1. Yes. So I just compute these things. So here I have used also actually a theorem that if you have a determinantal point process and you want to compute a finite dimensional distribution, you can actually compute them this way. It should not come totally as a surprise, because this determinant, that's sort of the observable with z1 to this, right? You choose the g appropriately. And this will be the z transform, for your finite dimensional distributions. But now we have m variables, and you just compute the probabilities by taking residue calculus, so that the residue is 0 in this way. Okay, that's a complicated expression. You have to think a little bit about this. And so I claim that if you do this, you can define these functions like this, and now you have to verify that Kolmogorov's conditions are satisfied. And it's very simple, actually. It's just a nightmare to work out all the conditions. But I want to do this. And now verify Kolmogorov's conditions.
What is exactly the exponent of z?
So okay, let me write it as maybe as the product over L is 1 to m of z to the L times chi of L at, chi of A of L. The indicator function that you are in the set.
Okay, but this indicator function is evaluated at
So it's not really evaluated, right? Because we take the determinant. You have to expand this determinant.
okay, so I see this as a certain function that will be multiplied by this matrix.
Yes.
Okay, in the sense.
Yes. So this is the determinant of the matrix. So if you put the matrix, then there will be an x here.
Yes,
and
okay.
Yes, exactly. Yes. So it's a little complicated expression. You have to get you have to round it a little. And actually proving the Kolmogorov's conditions is actually not very hard. What is the most difficult? Yes, maybe that's a good idea actually.
Yeah, probably it's calculation.
The most difficult condition, the most difficult thing to check is actually that these are positive numbers. They should be positive numbers, and I have a complex integral. Okay, and that thing I worked out in detail in the proofs, and the rest of the conditions are just similar. It's really notes, details are in the notes, but it's not a very difficult statement to prove once you have Kolmogorov's extension. And it's extremely useful, because now we can start just looking at our favorite self-adjoint operators and start working, right? So you take your self-adjoint operator that you like, and I will put on a few. And these are all determinants, and they all give rise to processes that are interesting. Okay, so and we will see next week. We will start also seeing several cases, but let me let me start with with some examples that I very much like. So.
Maurice, could you repeat the if and only if condition? Sorry, I probably missed something.
So it's if and only if the spectrum of K as an operator is between 0 and 1, including 0 and 1. So it just says it's a positive operator and 1 minus K is a positive. So this notation this inequality is between operators, which just means that 1 minus K is positive. Yes. So the spectrum is in. So maybe I could replace this by the spectrum of K is contained in 0 to 1 and including 0 and 1. Yes.
Can I ask a question?
Yeah, absolutely.
So this is all in the discrete setting where we have
Yeah.
this particle whole duality. So
Yeah.
is this sort of an analog statement in the continuum?
Yes.
Don't have this upper bound then?
So theorem, the particle Hodel duality doesn't matter. The same statement is true.
Okay, but you,
So-
so you don't have some.
You have also this condition. You also
Okay.
have this condition.
But there's no simple. Why
There-
would you
there is-
see it like this or?
So there is a reason why you need this, and you see it in the proof clearly. So to check that these things are positive probabilities, you have to manipulate, and this manipulation of the determinant really shows that you need an operator that this one cannot, you cannot go. You have to have this inequality. But for the particle whole, if it is discrete, it's already natural. And so for the continuous case, I don't have a good explanation and just look at the proof. Yeah. But if it holds for discrete, then by limits it should hold for continuous also. By continuity somehow, approximation. I don't know. Right. Okay, so yes. So let me now get to my personal favorite. I mean, this is definitely true. My favorite class of operators, and we will see them in many places actually in this course in different ways. So they appear all the time, but not in the same situations, in different situations. And these are operators, they are Duits operators. Okay, so I like those very much, and they will appear all the time. So let me start. I'm going to look at some operators, right? So let me start with saying I'm going to look at L2. First, I'm going to look at something continuous here. So this is just L2 on the circle. So this for me is, right, so this is just a circle. So just look at L2 on the circle. Now, given a function A, which will be also a function on the circle taking values in 0 and 1, define MA, multiplication operator, which acts on L2 on the circle to itself, and maps F to A times F, just multiplication operators. Okay, so you take a function, you just multiply the function by a function. And since the function is bounded, this is a bounded operator. So there's a bounded operator. It's a bounded operator, it's even it takes real values, right? Values between 0 and 1, but takes real values. So it's even a self-adjoint operator. It doesn't matter if A doesn't feel any conjugation. So MA is then MA is a self-adjoint operator. And I claim also the spectrum of MA is contained in 0 to 1. Is that obvious to people? Is that obvious? Maybe I need to say a word about that. Or is it obvious, or you think it's obvious? Or yes. I mean, it's sort of obvious because what you need to check is that if you're outside the spectrum, that you can, if you take lambda outside the spectrum, then MA minus lambda A should be invertible. But MA minus lambda A, that's just saying that, you know, this is just the M of A minus lambda inverse, right? So if lambda is not in the image of A, then clearly we can invert it, right? So yes. So this is really not difficult as long. So the spectrum of a multiplication operator is just the image of the function. It's sort of obvious. But you know, but things that become obvious, that are obvious at 5 o'clock, become suddenly extremely non-trivial. So MA is a self-adjoint operator. Okay, very good. So this is continuous. I don't want to do this. I want to look at this in the Fourier basis. Okay. So I want to now look at LA, L of A, which is just the matrix representation of MA in the Fourier basis, and I claim that this is the matrix A, J minus K, where J and K run from minus infinity to infinity, and AJ is just the Fourier coefficient of A. That's less obvious. Okay, maybe you check this, but I claim that LA, this is the matrix representation of MA in the canonical basis. Is it right? So C to the K and Z basis, orthonormal basis, the Fourier basis. Okay, and why is that? It's actually if you don't know this or you don't see it, it's simple computation. Do it at home. It's important computation to do it at home. I think actually, the thing is that multiplication in the usual domain is convolution in the Fourier domain, and that's just what it is. Okay, so. And I think actually it's a useful computation to do because Duits operators will come all the time. So I will just leave it to you. Okay, so, well, if A is a self-adjoint operator with spectrum 0 to 1, then the matrix representation is also a self-adjoint operator with spectrum 0 and 1 because it's just unitary equivalent, clearly, but it's just choosing the basis. So this operator defines a detrimental point process. Very good. So now, so we see the theorem, so any A that goes from the circle to 0 to 1 defines a detrimental point process with kernel K, so it's a detrimental point process on Z. Right? So we are really working on Z. Right? So it's on Z, and xy is just A of x minus y, which is just 1 over 2 pi I times the integral of AZ dz over Z AZ to L. Okay, I will violate my convention. Z to the x minus y plus 1. So, okay. So you can just now take examples, okay? Note that this is, you know, I don't do this just because they are my favorite type of operators. Oh, well, maybe one of the reasons they are my favorite type of operators is that this is actually a very nice construction. So for any A, I have a nice point process, the point process, and they all have a property that they are translation invariant. Note that they are translation invariant, and that's a very important property. What do I mean with translation invariant? I mean that the k of x plus, let's take a shift t, y plus t, is the same as k of xy. Right? I mean, obviously, because the value only depends on the difference, so if I increase x by t, then also. And that's a very nice process, right? So that means that the process doesn't really see any coordinates. It just doesn't matter where you put your coordinates. It's sort of, it's translation invariant. And it should, you know, and translation invariant is something you should expect in the limit when you look at, you know, you look somewhere in these random matrix examples that we had, right? For example, look somewhere in the build, look at the eigenvalues. Somehow, it doesn't really matter where you are. It should be translation invariant. And if you remember, we had the sine pi of x minus y over x minus y, which was translation invariant. And so this is a natural class of processes. Okay. Okay, so now I'm running a little out of time, I think, but that's okay. Oh no, I still have some time. Now I want to look at, and this maybe comes at the moment a little out of the blue, but I want to put one more property on my kernel, on my process. Okay, I want to put one more property. I also like not only self-adjoint kernels, I also like it when they are actually projections. Okay, so self-adjoint projections. They have very nice properties. I will get to it in a minute. Let me stay with this class first. What does it mean? Well, we already know that k star is k, right? So this was already an example of that. But I also want that k squared is k. Okay? Why a projection? So now this comes out of the blue. But you will see, especially next time when we start doing things, the random matrix and the tilings, they're all projections. Actually, the projection is more important than the self-adjointness. Almost all the processes that we will look at in this course will be projections, but not always self-adjoint. Okay, so this will become clear later. So I just accept now for the fact that this is a nice property to have. Okay. So which one of those translation invariant cases are actually projections? Well, projections. So for this case, well, then I need that a squared equals m of a. But multiplication by a, that's okay, that's a squared equals m of a. So what does it mean? A squared needs to be equal to a. Okay. Yes? A squared equals to a, that means that a is either 1 or 0. But this is a function, so at each point we can choose. So, okay, a nice example is when a of, let's say, z, right, is equal to 1, if the argument of z is between, let's say, t and minus t, and 0 otherwise, right? So if I look at the circle, a is 1 just on an arc, right? And then 0 outside that arc. That's a very nice example. And what happens? Well, in that case, right? What are the Fourier coefficients? What are the Fourier coefficients of z? Well, you can just compute them. They're going to be the sine k of t over k. And this example will give me that the k of x, y is the sine of t times x minus y divided by x minus y is actually an example of this case. And I claim so so this one is one to remember. We will see it. Don't worry if you understand it's late. So don't worry. It will come back. But this is a very nice process. We have the sine function. It really comes as sort of almost a unique translation invariant process, the determinantal point process that is also comes from a projection operator. So it's really a very, very nice one. How much time do I have? Okay, so I have 10 minutes. Let me say maybe in 1 or 2 words why projections are actually very, very useful. Okay, not why they appear, that will come next time, but why they are useful. Okay, and maybe actually from the properties you will actually see why they also are natural. So remember, so why do we like projections? Not even self-adjoint, but just projections. Well, let me remind you that we were looking at counting statistics. And when we had counting statistics, yes, and I look at the variance of the counting statistic, then I had a nice formula. It's the sum over x in A, kxx, minus the sum over x and y in A of kxy, kyx. Yes? Everybody, maybe you didn't remember, but you remember there was such a formula, and this is it. Yes? Okay. Now let's take a special case. Let's change this in the whole space. Let's just look at the number of points in my process. What is the number of points in my process if I take now x here, x here? It's a projection operator, so this actually is just equals k of xx. So the whole thing is 0. The variance of the total number of points in my process is 0. Okay, so how many points do I have? Well, that's the expected number of points in like this. This is the sum over kxx. Yes? So this is either finite or infinite. Okay? But it's fixed. And this is the rank of the kernel K. And this even holds not even for self-adjoint, just for projection. The only thing I used in this computation was k-squared. So if you have a process that has exactly n points, I bet that it comes from a determinantal point process, where the kernel is a projection operator, and the rank is n. That's why they appear everywhere. Okay, so there's even a nice, actually, there is even a nice 0-1 law which holds, there is a nice 0-1 law that even holds without projections. Here, actually, well, there's a nice theorem that I have in the notes that says that the number of points in the process is either finite or infinite with probability 1. Like it's a 0-1 law. So either it's always, you know, the number of points. Right? Because if you look at the, I mean, you look at probability measures on subsets. So it could be that that there is a positive probability of having finite number of points, and there is a positive probability of having infinite number of points. It could be, you know, some configurations might be finite, some could be infinite. Actually, what you can show for self-adjoint, it's not the case. It's either always finite or it's always infinite. And if it's a projection operator, then the number of points is finite. Okay. So okay, these were maybe a little too many small remarks at this time of the hour. But I hope that I made clear that you know that the projection operators are important. We will use the theory of determinant point processes quite a bit. So starting next time, I will give more examples just of determinant point processes and more examples of how to construct them out of the Aztec Diamond. Next time I will show the Aztec Diamond is one. It's a projection operator, one with a projection operator. It's not really self-adjoint, so that's a little annoying, but limits of it will in certain ways be self-adjoint, so we will see that. Actually, this limit that I have here, the special case, is actually a limit that we can see in the Aztec Diamond. So I will show that. I will show that not next time, but the lecture behind that. But this is the framework that we will be working on. Okay. So if there's no more questions or other questions, maybe. Yeah.
I'm confused by something very silly. Why is it equal to the rank of K?
Because this is the trace of the operator, and the trace of a finite rank operator is the trace of an operator is the sum of the eigenvalues, and the eigenvalues are 0 or 1 because it's a projection operator.
And in general, why is it so? So in general, this is supposed to be always an integer, right?
Yes. Yes, or infinite. Yeah.
So if you start with a self-adjoint operator.
No. It doesn't always have to be an integer. Sorry.
No.
It's only an integer if it's a projection operator. No, that's not true. If it's a projection operator, it's an integer. But because what you could have, and this definitely happens, is that the number of points in my process is not a fixed number. For some configurations, I have 3 points, while I have like 10 points. Like actually, this happens a lot when you look in statistical mechanics at the grand canonical ensemble. You actually average on all number of points. So this is natural that you could have configurations. And if you have that, then this trace does not have to be an integer. So the trace is only an integer if you are at a projection operator. Yes. And for a projection operator, the number of points is in the process is fixed. It's not a random number. But that's only for, you only can deduce that for finite rank operators, not for other operators. Sorry, for projection operators. Sorry. I hope I'm not confusing. Yes.
So when you consider MA, you say that MA is a projection, if A only takes the values 1 and 0.
Yeah.
But the set of points in which you take value 0 could be in not an arc, but something more general.
Yes. Yeah.
And then what kind of kernel do you?
Well, then you get, but then you will get some like linear combinations. I guess I have to think a little bit, but I guess you get some linear combinations of those sine functions with different t's. I guess because you can probably, if you would also have and it's sort of a linear, if you would also have an arc here or an arc there, you have several arcs, you just compute it, right? You get some, maybe, yeah, you get some, I mean, you just compute these pieces on these arcs. It will still be some sine functions. I don't know, yeah.
If it's not symmetric, you may have also a complex space.
Yeah. So you have a complex space, but actually I think that's a gauge. It's a gauge, yes. But you could have different gauges for different terms. So okay, so you get an answer. So to be honest, I have never seen how they appear as a limit. Now I don't know if doesn't mean they don't. Anybody in the audience has seen those as a limiting? There are, of course, they could appear, but I don't. Wait, maybe I have to think a little. Maybe there is a. I haven't seen them. I haven't seen them. Let me make then maybe one final remark about the way, like, if you see what happens when x and y are very large, right? This will always, in this translation of variant kernel, these are basically the only options, right, or linear combination. They will always go to, the correlation between x and y will always go to 0 with 1 over the distance, right, the correlation of 1 over the distance, right? So that's a typical behavior for these translation variant processes. However, I cannot remember. More questions? Yeah?
The last example, if the variance is 0,
Yeah.
can we conclude the point process is has a projection kernel?
Yes. That's actually, for self-adjoint operators, that's a very nice remark. Because the variance can actually be written as the trace of k minus k squared. Yes? That's what this is actually. If you take this variance is the trace of k minus k squared. And this should always be a positive number because k is, if it's self-adjoint, it's between 0 and 1, right? Only self-adjoint, right? Yeah, otherwise no. Self-adjoint, then this is always positive. So if it is 0, then we really need, right, because of positive, this operator is positive, then we really need that k minus k squared is actually 0, which means k squared is k. So yes. Very nice. No more questions? Okay. Very good. Then let's see each other next week again.